In this video, we'll continue to explore the basics of P4 programs. We'll discuss control blocks, tables, actions, and deparsing. At the end of the video, we'll complete our implementation of the basic IPv4 router and verify its functionality in Mininet. Aside from parsers, control blocks are the only P4 programmable elements in an architecture. These blocks are similar to C functions but do not contain any loops. We can declare variables, create tables, instantiate externs, etc. The actual functionality of a control block is specified within the apply statement. We can represent all kinds of processing that are expressible as a directed acyclic graph, such as match action pipelines, deparsers, and additional forms of match action processing. The interfaces between a control block and other blocks in an architecture are defined by both user and architecture-defined types, typically headers and metadata. Here is a very simple example of a control block that swaps the source and destination MAC addresses and then sends the packet back out the same port on which it arrived, hence the name reflector. We define a 48-bit variable called temp to hold the current destination MAC address while the swapping is taking place. This temporary variable is local to this particular control and cannot be accessed by other blocks. We could have also declared the temporary variable inside the apply statement to achieve the same functionality in this case. The reflector can also be implemented by defining a simple action called swap MAC and then invoking the action directly within the apply statement, similar to how you might invoke a C function. These actions can be declared either inside a control block or globally. Since this action is invoked directly within the apply statement, each action parameter must specify both type and direction. Actions may contain local variables and may make use of many different standard arithmetic and logical operations, as shown here. Tables are the fundamental unit of a match action pipeline. A table declaration will specify a number of different things, including what data to match on, the type of match to be performed, a list of all possible actions that can be invoked, and it may optionally specify additional table properties such as the number of entries, a default action to invoke if no match is found, or static table entries. Each table contains one or more entries, commonly referred to as rules. A single entry contains a specific key to match on, a single action that is executed when a table matches the entry, and any data to provide to the action when it is invoked, which may be nothing. Let's walk through the steps involved in performing match action processing. As we just mentioned, our table consists of a number of entries that specify a key, an action ID, and action data. These entries can be added and removed by the control plane. A table will also specify a default action to perform if no match is found amongst the table entries. The table will extract the specified bits from the input headers and metadata to form the key and attempt to find a match within its entries. If there's a hit, then the action ID and data are read out of the corresponding entry. If there is not a hit, then the default action ID and data are used. These two outputs are passed into a multiplexer, which selects one of the two based on whether or not a hit was found in the table. The chosen action ID and data are passed to the action execution unit along with the input headers and metadata, which then modifies them as necessary. To build our simple IP router, we will need to define a routing table. The routing table must perform a longest prefix match on the destination IP address. Each table entry may invoke either the IPv4 forward action, which updates the packet's destination MAC address, configures the packet's egress port, and decrements the TTL, or it may invoke the drop action. The default will be to perform no action at all. In the example provided here, if a packet comes in with a destination IP address that is equal to 10.0.1.1, then the table will invoke an action called IPv4 forward, providing as input the destination MAC address and port number shown here. On the other hand, if a packet arrives with the destination IP address that matches 10.0.1.2, then it will be dropped. I want to take a moment to highlight how the data plane and control plane work together to perform IP routing. The P4 data plane defines the format of the routing table. It specifies the fields to match on and possible actions to invoke. It performs the table lookup and executes the chosen action. The control plane is responsible for populating the table with entries. There may potentially be many different control mechanisms for manipulating the table entries, for example, network operators manual configuration, automatic discovery, or routing protocol calculations. Both of these planes must work together to make IP routing work properly. This is what the routing table that we just described would look like in P4. Here we call the table IPv4-LPM. As you can see, the key is the IPv4 destination address, and we specify a match type of LPM, which stands for longest prefix match. The second table property is the list of all possible actions that can be invoked by this table. In this case, the possible actions are IPv4 forward, drop, and no action. We also specify that the table should be allocated with enough room for 1024 entries, and the default action should be no action. Tables can specify various different match types. Core.p4 defines 3 types that all architectures should support: exact match, ternary match, and longest prefix match. Other architectures may define additional match types that can be used in P4 programs. For example, the V1 model defines a range type and a selector type match in addition to the 3 standard types. We have already seen how you can define actions and invoke them directly from a control block's apply statement. And based on the discussion we just had about tables, you are probably already aware that actions can be invoked from tables as well. Actions can have 2 different types of parameters corresponding to these 2 ways of being invoked. Directional parameters are those that are passed from or to the data plane, and directionless parameters are those that are provided by table entries, or in other words, from the control plane. Actions that are called directly only use directional parameters, and actions that are used in tables typically use directionless parameters, but may also use directional parameters. Here on the left we show the declarations for the actions that we will use to build our basic IP router. Note that the parameters for the IPv4 forward action are directionless because it will be invoked from the routing table. After defining the table, it must be applied within the control flow. This is done by invoking the table's apply method, as shown here. We can also use a control block to implement the deparser. Deparsing involves assembling the headers back into a well-formed packet. We can use the emit method of the packet out extern to insert a specific header into the final packet if it is valid. Now let's try to complete the implementation of our basic IPv4 router and test it out. We have already completed the parser, so now we have to finish the ingress control logic. This example does not require the egress control block to do anything, and the checksum update logic has been provided for us in the starter code, and we have to complete the deparser. So let's examine the starter code that's provided for us in the ingress control block. We see that it applies one table called IPv4-LPM, which is defined here. This is the same routing table that we've been discussing throughout this tutorial. The IPv4-LPM table can invoke 3 actions: IPv4 forward, drop, and no action. No action is defined in core.p4. The drop action has already been implemented here in the starter code, so all we need to do is complete the implementation of the IPv4 forward action, which must perform 4 operations. It must set the egress port of the packet to the port number provided by the control plane, and we do this by setting the standard metadata egress spec field. It must update the packet's source MAC address with the MAC address of the switch, or in other words, the packet's current destination MAC address. And it must update the packet's destination MAC address with the address of the next hop, so that's the address provided by the control plane. And finally, it must decrement the TTL field of the IPv4 header. Now, all that's left to do is to complete the deparsing logic. So for the deparsing logic, all we have to do is emit the Ethernet header into the packet and emit the IPv4 header into the packet. Now at this point we have a fully functional data plane for the basic IPv4 router. The testing infrastructure for this exercise implements a static control plane that simply adds a couple of entries to the IPv4 LPM table on each switch. So let's take a quick look at the table entries that will be added for switch 1. The first line sets the default action of the table to drop. Each of the subsequent entries specify an IP address and prefix length key and indicate that the table should invoke the IPv4 forward action, where each provides a different MAC address and port number to the action. Now we will try to compile the P4 program, and we do that simply by typing make build in the project directory. After the compilation succeeds, we can type make run to start the Mininet network and add the table entries into the switches. And from the Mininet command line, we can fire up two Xterm terminals, one on host 1 and the other on host 2. We will use Python Scapy to send a packet from host 1 to host 2. First, we start the receiving script on host 2. Then we can send a packet to H2's IP address from host 1. The packet will be sent to 10.0.2.2 and it will say P4 is cool. We send the packet and we see that it does indeed arrive on host 2, indicating that our switches are forwarding properly.